All right, we're going to do an example problem using Bernoullis equation. So here we have water going through a tube. Down here at position 1, it's going at 5 meters per second. The pressure is 75 kilopascals, and the radius of the tube, the circular tube, is 3 centimeters. Then the water goes up 2 meters, a vertical 2 meters, and the radius changes to 2 centimeters. And we need to find volume tube and pressure tube. So to do that, we are going to first use the continuity equation. And for the continuity equation, we know that area 1 times velocity 1 is equal to area 2 times velocity 2. Now, area 1 is going to be the area of the circle, which is pi times the radius squared, so 0.03 meters squared, times the velocity, which is 5 meters per second. And then that is equal to, look at me, I'm breaking my own rule here. I didn't isolate my unknown variable. So I know both areas and I know the velocity at 1. So to find the velocity at 2, I need to solve isolated velocity at point 2. So V2 is equal to A1 V1 over A2. So that's what I'm going to do here. I'm going to divide by A2, which is pi times 0.02 meters squared, and that is equal to 11.25 meters per second, because our pi's cancel out there. And so that's our velocity at point 2. So now once we know our velocity at point 2, we can use Bernoullis equation, which is P1 plus 1/2 times rho, which is density of the fluid, times velocity 1. I'm putting a little thing on the velocity V, so you know it's different than the volume V, plus rho g h1 equals P2 plus 1/2 times density of fluid times velocity 2 squared, plus the mass times gravitational field strength times height 2. So now we are solving for P2. So I'm going to isolate P2 here by subtracting over this term and this term. And when I subtract this term over, the 1/2 and the rho are the same, and then your velocities are different. And then when I subtract this over, oh, I put an M. That's supposed to be a rho. Okay, so we get P2 is equal to P1 plus 1/2 times the density times V1 squared minus V2 squared plus density times G. Goodness. Oh, that's not quite what I wanted to do, but that's okay. All right, density times G times H1 minus H2. And then from here, we can plug in our numbers. And before we do that, we have to think about what the pressure is. So this is given as my pressure in kilopascals. So that's the pressure in my tube here. But we want to make sure that we're using SI units, so we don't want to use the kilopascals. We'll put it in pascals. So we get P2 is equal to 75,000 pascals plus 1/2 times the density of water, which is 1,000 kilograms per meter cubed, times velocity 1, which is 5 meters per second. We're squaring that, minus velocity 2, which was 11.25 11.25 meters per second. Then we add the density of water, 1,000 kilograms per meter cubed, times G, which is 9.8 newtons per kilogram, times the change in height, which is 2 meters. Wait, it's height 1 minus height 2. So you would do 0 minus 2 meters. Oh, somehow I got back on the... I think I went too far on my tablet and then got the eraser. I don't know that you can see what that says. Okay. Try this one more time. I'll just put it down here. Okay, so then we would calculate that out, which I don't have done on my paper for some reason, but you would calculate that out and you would get a number, which I'm not going to take your time to do that. So that's an example of how to use Bernoullis equation.